EET 105, Chapter 2, Current and Voltage Notes. Coulomb's Law. The formula is F equals K times Q1 times Q2 divided by R squared, where F is the force of attraction or repulsion in newtons, and K is Boltzmann constant, which is always 9 times 10 to the ninth power Newton meter squared divided by Coulomb squared. Q1 and Q2 are the charge of two particles involved, and coulombs, or capital C, and R is the distance between particles in meters. It always has to be meters for this formula, so if you're given anything other than meters, you have to convert to meters. Current, it flows. The variable for current is always going to be I, and the formula is I equals Q divided by T. It's the change in current over the change in time. You might also see it written as I equals dq over dt, or delta q over delta t. Q is the charge of electrons in Coulomb C. T is time in seconds, always in seconds for this formula. E minus is the charge of one single electron, 1.6 times 10 to the negative 19th coulombs, a very small number. The number of electrons in a single coulomb is 6.242 times 10 to the 18th, which is basically 1 over this number here, as you can see up at the top of this formula. So that's a really large number. I is the electric current, flow of electrons in amperes A, or coulombs per second. Another concept is voltage. It's the potential difference. It's measured between 2 points. The formula is V equals W divided by Q, where V is the electric voltage potential in volts or joules per coulomb. W is the work or energy in joules, capital J. Q is the charge in coulomb C, and E would be a voltage source in volts also, capital V. The difference between V and E being this would be a source in the circuit. V can be any voltage in the circuit. Applications of these things would be example flashlights, batteries, or chargers, any kind of charger. Fixed DC power supplies. The life equals the ampere hour rating divided by the load in amps. So life being the battery life in hours. Ampere hour rating would be the battery capacity in amp hours, or AH. And the amps load is the required load in amps, A, capital A. Conductors and insulators. Conductors conduct electricity. Example of a conductor would be copper, aluminum. They have a temperature rating and a current rating depending on their cross-sectional area and their actual conductance changes based upon temperature. The relative conductance is related to which material is being involved in the conductance of the electric, the flow of the current. And insulators, typical examples will be rubber or plastic composite around wires, and they also have a temperature rating like 60 C or 75 C or 90 C. Multimeters would be used in a lab if we were doing an in-person lab, and they're used for measuring primarily resistance, voltage, and current. Mechanical, electrical analogies. To get familiar with these concepts, we would think of something like what we're familiar with. Charge would be electrons would be equal to the water or the fluid involved in the system. Voltage would be the pressure, like if you have pressure in your pipes, 70 psi, that's the voltage. Current is the actual fluid flow. So if you turn your faucet on, you have fluid flow, you have current. When you shut it off, you have pressure there, but no current. Resistance would be pipe frictions or losses. The conductor wires would be like the pipe. Valves would be like the switches. involved in the circuit. And an example of a capacitor, which we're going to get into later, would be an accumulator in a mechanical system. So think of fluid flow through a pipe or a waterfall. When the water falls down, it's flowing. That's the current flow. And the difference in the height from the top of the falls to the bottom would be the voltage. And the rocks would be the resistance. And the river or whatever it's flowing through would be the conductor.